So this video is about how minimal discriminants how they change under base change. Okay, and just kind of a thing about relations of minimal discriminants and tape parameters in general. Okay, so the first fact is that so we're going to fix so we're going to fix E over F, an elliptic curve. And the thing that I want to say is that places of good reduction, of good or multiplicative reduction, are stable under base change. So if I extend the field, you're not going to get worse, right? It could be the case that places of additive reduction, I just want to remind you this, can change. And they will change under some extension. And will change under some extension to good or multiplicative. Under some extension. Okay, let me remind you of the definition that says that if all places, if all places of E over F have good or multiplicative reduction, then E over F is called semi-stable. It's called semi-stable. Okay, it's called semi-stable because when you base change, the type of reduction does not change. Okay, so another fact that we will need is that so if E is an elliptic curve over K. Okay, and K is a complete discrete valuation field with valuation V. Okay, and I'll write it as ORD V. Then the fact that the J invariant is bigger than 1 means that there exists a Tate uniformization. QE. So first of all, there exists a Tate. There exists a Tate parameter. So this is the Tate parameter. And so let's just say there exists this. Let's write it like this. There exists a Tate uniform. There exists a Tate parameter. Okay, so there's this number. Okay, and uniformization map. So these are special elliptic curves here to EQ. So this is defined over K-bar. Okay, so this is in Silverman Advanced Topics, section 5, lemma 5.1, if you want to go see this. Okay, note that this implies that, note that this implies the following, that all elliptic curves over this complete discrete valuation field, all elliptic curves without potentially good reduction have a unique Tate parameter. Okay, at the bad places. Right, so the bad place will be not potentially good. Okay, and and actually we can say a little bit about what the tape parameter is. So in fact, um, we know that this tape parameter here, it's a rational function in here. So let's say so here we'll say that K is an extension of QP. Okay. So yeah, so there's a expression for Q of E in terms of the tape parameter. Okay. So now I want to explain a lemma. And this is how tape parameters are related to the minimal discriminant of an elliptic curve. So if E over K is an elliptic curve, over K is a complete discrete valuation field, then we have the following. So if E has multiplicative reduction, right, then this implies that the valuation of the minimal discriminant is equal to the valuation of the tape parameter. All right, and then the second thing that I want to say is that all these things are minimal Weierstrass equations. Okay, so they have minimal discriminants. All right, so how do we prove this? So let's do the first proof. So proof of 1. Okay, so so we want to show that the minimal discriminant is the same thing as the order of the valuation. To do this, we use Ogg's formula. Ogg's formula states that the local conductor, so this has to do with Tate's algorithm and this sort of thing. Okay, plus 1 minus mv. Okay, so this is the local conductor. This is the order of the minimal discriminant, and this thing here is the number of irreducible components of the Néron model of E over K. Okay, and in our application, so what are we doing? So E has multiplicative reduction. So in the multiplicative reduction case, this is 1. So in the multiplicative reduction case, this thing's equal to 1, right? Which tells us that here, so this implies that ord v min is equal to mv, the number of irreducible components. Okay, so next, this is the one step. The next thing we have to do, and so this is the back of Appendix C, Baby Silverman, right? Okay, it says that so we'll let the Néron model here of E over K. This is E, and this is a scheme over OK. Okay, and what we have is that. So let me give a proof of the second part. All right, and so so this is really simple. It says that, so we have delta looks like Q, so there's this development like so, and so here the p-adic absolute values are the same. So you can see that has a leading term 1. Okay, so that's what we have. So here's a question, is how does the minimal discriminant this is the question that we had, change under base change. Okay, and so how does the okay, and so the next question is, we could ask, how does the minimal discriminant relate to the divisor associated to the tape parameters? Okay, and so let's take a lemma. So let K over F be an extension of fields. So we'll let E over F be semi-stable. Then we have the following formula. It says that here, if I take the norm of the minimal discriminant of E over F, right, and then I multiply this times the degree from K over F. So this is the natural log of the minimal discriminant from E over K. Okay, so that's what we get. All right, let's give the proof of this. All right, so let's do the proof. Okay, and so we're going to fix K over F a finite extension. And for the moment, let's consider that okay, so let's take this delta min EK over K, right? So this will be the sum of the places of K. And what we'll do is we'll take the valuation of the minimal discriminant. Then we have to use the inertia degree because that's part of the norm. This is W over P, and then natural log of P. So I guess this is PW, natural log of PW. Okay? That's what we have here. Okay, so we'll use that this thing here is the same thing as the tape parameter here. And we could write, let's write W here. Okay? And then we have FW over PW, natural log of PW. And then what else can we do? So then we could break this up further. Right? So let's do it like this. So this is so we have this degree. So this is E. So this is the same thing as E W over V, or V Q QW, but QW is the same as QV. Because once we have that it's that it has a tape parameter at a place of bad reduction, all the places above it will have the same tape parameter, right? And then this can be written as, this one can break down as well. So this will be W over V, F of V over, and then PV is the same thing as PW, ln of PV. So these are the same thing. And I guess we could write, we could break up the sum a little bit. Let's break up the sum, and we'll write the sum as here W dividing V, and then we'll write V in VF. Okay, so that's this whole thing. So we have this double sum here, same double sum as down here. I'm just being lazy. Okay, so now these two things go together, and this is the degree of K, like this. Oh, sorry, KW over FV. Then we have ORD VQV, FV over PW, ln of p v. So sorry, we have v over pv. PV is, of course, the rational prime associated to the base. So these two have the double sum. This thing here, so this thing is just, so when you sum over all the places above, and you take these degrees here, so this is just k, the sum is just k over f, and it's a constant, so you can just factor it out. All right, and then we have this sum here, v in vf, or vqv, fv over pv, natural log of pv. And then this thing is exactly like the same definition we started with, I guess, at a different level. So this is, so this whole thing is k, this degree, natural log of the minimal discriminant of e over f. Okay, so that gives us the formula that we wanted to show here. Okay. Okay, so I want to explain how the Q-pilot, Q and theta pilot divisors are related to the minimal discriminants and each other. Right. The first assertion is that the degree. So here. Okay. So this is. So we're going to fix E. E is an elliptic curve over F. Okay. F naught's the field of moduli. And then we're going to pick K. So F over F naught is Galois. So I just want to remind you that K over F is Galois as well. Okay? And then this thing is sums over bad places. So these are all the places that are not potentially good, right? So this is the definition of the Q-pilot divisor. And what we do is we take the order of the tape parameter, the nth root of the tape parameter at V, and we slap it on there. So this thing here, the double underline is, this is 1 over 2L. And then I also want to make the remark that since the tape parameter is an absolute invariant, that doesn't depend on the lift. Here, so this is in here, and so this is a lift of the, so each place of the field of moduli has a lift to this other field extension. Okay, all right. So this is the definition of the Q-pilot here. Okay, and so let's just start with the first claim. The first claim is that the first claim that we want to show is that the normalized Arkelov degree here of PQ. So this is equal to 1 over 2L times the norm of the minimal discriminant. And since minimal discriminants are invariant under base change, well, not quite invariant under base change, but they're invariant up to, so here we can base change this over K. So if you divide by the appropriate degree, same with our Arkelov divisor. So we have that these all these things are the same here. I guess the point is that this thing could have some bad places, some places that will have additive reduction, right? That turn into good reduction after base change to F. So we don't deal with the minimal discriminant of the field of moduli. So let's give a proof of this claim. Proof. Let me convert back here. All right, and so the proof is it's kind of straightforward. So we'll take the degree. So let's just take the degree of this Q-pilot divisor. Okay, and so let's just do it in terms of, so I divide by 2L there? Yeah. Okay, so so let's do this. So this is, well, these are all the bad places, right? And so we'll do it without the double underline. Okay, so that's you know, the double underline is just the 2Lth root. Okay, so we have this situation, right? Okay, and now let's pull this thing back all the way to K. Right, so this is W. Let's keep it like this: V bad, and then we keep this the same, and then this thing becomes, we get a ramification index, and then we get one of these. So W is a place of VK. All right, now we can combine these. All right, and so this is a sum over V. This is a place of F still. And then we have the sum of W dividing V. So W and VK now. So these are placed in VF here like this. And so these two things get to combine to give you the order of W of Q of V, W like so. Okay? All right, so that's no big deal, right? And so this thing here, so we have all the places now, so this is here, and now we're just summing over W bad of ord W Q. And so, okay, so the other thing is that these things are absolute, so this is QW. Oh, right, W. Okay, and so by the lemma, so this is the degree of K of sum over W bad, and now this is the minimal discriminant. EK over K W. Right, and we saw that this is so the degree, so this is just the degree divided by the degree. So the bottom is just the degree. And then the top is the log of the minimal discriminant, like so. So this is just like an elementary computation. Okay. The other part, so the other thing is that so the other part was, we already proved, was that this was invariant under base change. So we could also use the field here, E over F. Okay, so we have this one too. So this is same idea. Okay.